Hello, my name is Atkinson, and I'm a researcher into mass extinctions. These events are rather like the ultimate murder mystery, worthy of Agatha Christie herself. Today, we're going to explore the case of the end Triassic. We're going to work through the evidence, line up our suspects, and give our final verdict. So, let us begin our tale in the familiar settings of Lyme Regis. It'll be little surprise to anybody to learn that the rocks around Lyme Regis are predominantly Jurassic in their age. However, if you travel west of the town due to the dip of the beds, you'll find older rocks, and this includes some of the Triassic, the period preceding the Jurassic. So the boundary interval is preserved on this coastline. It's a particularly exciting boundary because it is also associated with a mass extinction event. The end Triassic mass extinction at 201 million years ago. This is one of the big 5 mass extinctions. These are periods of great catastrophe in Earth history that have knocked back the evolution of life, and then it's had to sort of bounce back from that. And the end Triassic occurred during this sort of bounce back from the biggest mass extinction ever, the Permo-Triassic, 251 million years ago. So this is the one we're interested in, the end Triassic mass extinction. And we're going to go and look at some of the details of this and try to work out what happened. On land, lots of creatures died out. About 22% of terrestrial families were wiped out at this time. And one of the groups that were included with that was some of the archosaurs, phytosaurs and the heterosaurs, and these are considered to be competitors of the dinosaurs. And the removal of these from the ecosystem is thought to have allowed dinosaurs to radiate during the Jurassic and become that dominant beastie that we all know and love. In the ocean, it was just as bad. About 23% this time of marine families died out. And this included a great number of seashells, like these large bivalves at the bottom there, megalodontids they're known as, not to be confused with the big shark megalodon. Also, this extinction wiped out the conodonts. These are very small fossils that are like jaw elements of beasts, a bit like a hagfish, really. They're very useful to date rocks with. They evolve very quickly. So unfortunately, if you like to date your rocks using conodonts, this is the extinction that removes that opportunity from you. Something else that happened is the plankton had a bit of a going on, really. The radiolarians, these are microfossils. They're a plankton, and they have a shell made of silica. At this extinction, you lose all these exciting forms at the bottom of this image. You see them here with the TR, that's for Triassic. They look like little spaceships and bells and all manner of things. But when you go into the Jurassic, they just look like sort of golf balls, really. They're not as exciting. Something goes on there. And also produced a reef gap. This mass extinction affected coral reefs particularly badly. It's probably one of the worst extinctions for the Screllectinian corals. They're the corals that we have today. This mass extinction produced about 10 million years of reef paucity. There's not many reefs at this time because of this event. So, what did it? Who's guilty? Was it a meteorite that caused this? Like with the end Cretaceous extinction, the one that clobbered the dinosaurs? Or was it volcanism, like with the Great Dying, the end Permian mass extinction? Was it a large volcanic province that caused the end of the Triassic? Well, this is what we're going to try and work out tonight. So let us begin with the meteorite. First off, how can a meteorite actually cause a mass extinction? Big great rock falls to Earth. What happens next? Well, I guess if you're unlucky enough to be standing underneath it, then that's probably going to kill you. But it's not going to cause a mass extinction itself. What it is the dust. Dust gets brought up into the atmosphere and it causes a darkening. It reduces the effectiveness of photosynthesis of plants. And then once your plants start to die back, your food webs collapse. So it's kind of knocking down the tower of cards from the bottom. There are other effects, of course. If it lands in the ocean, it's going to cause a big tsunami. That's going to cause some havoc if you're living near the coasts. Also, when molten rock that was blasted up into the atmosphere rains down, it can heat the air to intense levels that can cause forest fires and just cause animals to die of heat. So it's a pretty nasty thing as a large meteorite. But note, it has to be a large meteorite for all this to really go on. What clues can we look for to find out if a meteorite caused the end Triassic mass extinction? Well, here are the 4 big things that you can look out for. One of them is the ejecta layer. So this includes spherules of glass, or tektites. These are bits of rock that were blasted into the atmosphere when the meteorite impacted, and they rain back down as molten rock, and they cool so quickly that they turn to glass. So we can look for those around the extinction layer. Something also we can look for is shocked quartz. Shocked quartz sounds a bit odd. You make a bit of quartz jump and it goes, ah! No. This is where it's been hit by the meteorite and it's changed the molecular structure of the crystals. And again, like the glass spherules, it gets blasted up into the atmosphere and it trinkles around all over the place. And you can find these sorts of things at boundary intervals as well. Very small fragments of quartz. And then another thing is iridium. So this is a rare element on Earth, but it's quite enriched in some meteorites. So at the Cretaceous Paleogene boundary, the extinction there's a big spike in iridium in this sort of boundary clay. So you can look for iridium. Other things, Fern Spike, I'll come to that later. A seismite, this is sort of shaking up of the sediments, you can look for that. You imagine smacking a great big meteorite into the earth, it's going to shake things a bit. And also, you can look for the impact crater itself. Now, this isn't always the be-all and end-all. These things can get filled in, they can get eroded. You're not necessarily going to find it. But we'll have a look and see what we've got for this particular event. So starting with the ejectite, the layer of debris raining down from the atmosphere after the meteor has blasted things up. Well, there is one. This is from Bristol. It's in the Triassic, and there's a close-up view of this rock. It's been cut through and polished up. The close-up view on the right-hand side of the screen there, and you can see these little green circles. They're the little spherules of molten glass that rain down. It also contains shocked quartz, which is rather handy. So it's looking good. Yes, brilliant. But this ejectite isn't related to the extinction event, unfortunately. It may be in the Triassic, but it occurs many meters below the extinction horizon, unfortunately, in much older rocks. So still Triassic, but not related, unfortunately. So we thought we had a clue there, but maybe not. So the next thing we can look at is iridium. So as I said before, this is a very rare element in the Earth. Your average piece of crustal rock contains 0.02 parts per billion of iridium. So that means for every 100 billion grains of anything, you would have 2 grains of iridium. So it's very, very rare. If we look at St Audrey's Bay in Somerset, which also preserves the boundary interval of the Triassic and the Jurassic, we can see a slight rise in the amount of iridium, 0.4 parts per billion. So it's above average, but it's not particularly abnormal. Also, we look to America, we can see a slight increase at the boundaries again, 0.29. If we compare this to the end of the Cretaceous, the extinction there, which we believe was caused by a meteorite, the anomaly that produced was 29 parts per billion. So it's an order of magnitude, 2 orders of magnitude, in fact, larger than the Newark Basin spike. Iridium can be accumulated through other processes, it can accumulate if there's low sedimentation rates. So you're just sort of building it up progressively rather than burying it quickly in the rocks. So maybe that's what's going on in New Atkinson Georges, and it may not be related to meteorite at all. It's just not a big enough spike, really. So let's just review the clues. Spherules of glass. We didn't find them at the boundary, unfortunately. They were below it, remember. Shocked quartz, again, far too below the boundary. There is an iridium anomaly, as we just said, but it's maybe a little small. So we'll put a small tick in the box for now, and we'll see what we can come up with for other clues. Fern spikes now. What on earth do I mean by a fern spike? Well, if you look at the rocks under a microscope, you dissolve them up, and you can find pollen grains, or spores in this case. Now, the picture on the left there is a picture of a fern spore, and you can count these, and if you get an abundance spike, that's what we mean by a fern spike, an abundance spike of these, then it probably means the environment local to where your rocks were being deposited had an awful lot of ferns in it, and they kind of dominate the assemblage of pollen and spores. The idea being that after some sort of environmental disturbance, like massive meteorite shutdown of photosynthesis and collapse of food webs, the first things that tend to come back are the ferns. Like sort of clearing a patch of your garden and letting the soil do its own thing. You always get the weeds coming first. You don't get the nice lawn just turning up out of the blue. So it's these sorts of things that the ferns that are growing in this destroyed environment soon after the event. And the first things that colonize the land instead of trees and forests, which take much longer to re-establish. So do we see a fern spike at this interval? We do indeed. It's recorded in various places around the world, so that's looking quite hopeful. So yeah, big tick for fern spike. Next one, the Seismite. Now this slightly grainy image is the boundary in South Wales at Lavernock Point. Now the big sort of pale grey unit you can see in the middle of the photograph is the boundary beds, is the Cotton member of the Lilstock Formation. Now if you look closely at that, you sort of see some bedding in the bottom of it, nice layers of rock, and then there's a bit at the top that's nice and layered. But the stuff in the middle, it's a bit of a mess. It's all over the place. There's no clear bedding going on in there. So what's going on? If you look at it closely, and the picture we have here is actually from a different location in Northern Ireland, the bedding is all distorted and overturned and bent and buckled. Normally beds lie flat, not like this here, with my finger or some small gastropods down at the bottom there for scale. So what's gone on? This is the seismite, the shook up sediment. When something has gone on, like the meteorite maybe, has impacted, it's caused a massive earthquake and it's disturbed all the sediment, shook it around. Now this has to be a very specific type of sediment to work, though. It's got to be quite wet to really shake it up and get this distortion. So we have a seismite. Brilliant. Do we have a suitable impact crater? Well, we've got a bit of a list we can choose from. There's the Manicouagan crater in Canada, Saint Martin, also in Canada, Rochechouart in France, Obolon in the Ukraine, Wells Creek in America, Red Wing Creek in America. There's several other pathetically small ones that we won't go into, but this is the list of 6 we're going to consider first. So, some of these craters are fantastic. You can see them on Google Maps if you like. The Manicouagan is brilliant. It's absolutely colossal. Here it is making a lake in the crater rim, which is absolutely wonderful. And then if we look at Wells Creek, now first glance of this image, you might not necessarily be able to spot it, but can you see the sort of brown mountainous areas? They're kind of broken up with a nice ring in the middle. If I put a circle over, you'll see it where the fields are. That's the crater for Wells Creek there. Not all of the craters are nicely visible from photographs. Believe it or not, in these two images, there is a meteorite crater. You can't see it because it's been infilled, but you can find the rocks that suggest that it was there, this sort of molten mess and debris of the crater ring and big blocks that have been thrown up by the earth when it's smashed in. So if I put the outline of the crater on, there's no indication there from the surface that there's a meteorite impact crater. So with these craters, there's a little bit of a curiosity. If we take the continents and rewind them and put them back into their configuration when they were during the Triassic in the supercontinent of Pangaea, these meteorite craters seem to line up around 28 degrees north on that sort of ring of latitude. So, is this a coincidence? Or was this some sort of bombardment of meteorites that just struck one after the other, boom, 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 boom? Yeah. Well, if it was like that, then maybe it doesn't matter that some of these are very small. If you've got a big amount, a large amount of one after the other, maybe that's enough to cause the extinction. To prove that theory, we need good dating evidence for them. So let's have a look at what dates are available for these craters. So the little white circles are the crater dates, the grey bars are the error bars on those dates, and then the names behind them. The red line is the extinction horizon. So let's start by looking at Manicougan. Well, that's a good 13 million years before the extinction event. That can't be related. Same with Saint Martin. It's far too old. Oberon, that's too young. It's happening in the Jurassic. So that leaves us with we'll cross them out first, can't we? Then that leaves us with Rochechouart, Wells Creek, and Red Wing. Red Wing, only the error bars clip the extinction horizon. And also, if we look at the size of it, it's 9 kilometers wide. It's a very small crater from a very small meteorite. It probably wasn't big enough to cause the havoc we'd expect from we see at the mass extinction. The other one, Wells Creek, all I have on there is the error bar. It's got a terribly dated crater. There's 100 million year error bar either side of 200 million years. So I think we can probably discount that one. That leaves us with Rochechouart. Here it is. I've sort of put the theoretical maximum size of the crater onto a map of France. It's reasonably impressive. But not if you consider it to the impact that took the dinosaurs out. That's the Chicxulub crater drawn on in red there. This Rochechouart impact, it's still quite small, really. So was it big enough to cause the extinction? Well, we're going to leave that one on a sort of a hanger there. And we're going to go and look at volcanoes now. So this is a reconstruction of the Siberian traps, the big volcanoes that took out lots of life at the end of the Permian. Hence why there's a sea scorpion. The bottom sea scorpions weren't around in the late Triassic. So, what does a volcano do that can cause a mass extinction? This is a lovely plot. It shows all the different sort of things that go on, the cascade of effects from a large igneous province. So these are big volcanic regions. And the things to really note and highlight in red here, these are the sort of kill mechanisms. You can have things very similar to what a meteorite can do. Volcanic darkening, cooling, and shutting down of photosynthesis. Acid rain. I mean, that can damage the foliation of plants. So it can also cause a shutdown of photosynthesis and a crash of the food webs. Toxic metals, that's a nasty one. Yeah, lots of these things pump out some horrible metals. But the main thing that people associate with large igneous provinces is global warming from emission of gases. So I suppose what I'm sort of trying to stress here is on that list, lava doesn't show its face. That's not the thing that does the damage. It's the gas. The gases sort of affect the Earth in different ways over different time spans. The thing that we're most likely to pick up in the fossil record, the geological record, is evidence of global warming. That occurs over a much larger span of time. There is an initial cooling caused by sulfur gases, and that's pretty short-lived. It may not actually show up in the geological record. It's too short to be detected. So what clues can we look for to see if there was volcanism involved in this mass extinction? Well, the first one is Mercury. Bit of an odd one, I know, but we're going to have a look at that. Volcanoes give out mercury, which sounds horrendous. We don't know mercury, it's awful stuff. And so we can look at the rocks and see if there's evidence of a hyped amount of mercury in the environment at the extinction horizon. And this work here shows in red the amount of mercury in the rocks. And yes, at the boundary, in yellow, this time dashed in yellow, there is a big spike in mercury, suggesting that there was indeed a large amount of volcanic activity going on at the time of the extinction. So, tick in the box of mercury. Next one, evidence for increased atmospheric carbon dioxide, or CO2. What can we do for that? Well, first off, let's have a look at where that actually comes from. The volcanoes themselves emit carbon dioxide, one of the gases they give off. But there's another source that could potentially be larger than just the magma itself. And that's the burning of the rocks as the magma comes up through the crust. That can release carbon dioxide, especially if it's burning through some organic rich sediments. Any coal in it, for example, it can burn through that, release that, and that can also release the sulfur and things like that as well. And also some mercury can be released too from the rocks through this burning process. So it's not just the magma itself, it's also the burning of the rocks that can release these gases. So, a bit of carbon chemistry for you now. How can we tell that there was a change to the carbon dioxide in the atmosphere 201 million years ago? One thing we can do is look at clues in the different types of carbon. So there are sort of three types of carbon 12, 13 and 14. These are different weights. The number just refers to the weights of the carbon. They've got different amounts of subatomic particles. The two that we're interested in is 12 and 13. 14 you may have heard of. It can be used to date things in archaeological context. So carbon 14 dating, you may have heard of it on Time Team and things like that. So yes, these 12 and 13 we're interested in. Now the carbon dioxide that's released by volcanoes, or this baking process, is particularly enriched in the lighter form of carbon, carbon 12. Well, that's all very well and good, but now how do we actually look at that in the geological record? Well, rocks contain carbon. They draw this sort of down from the atmosphere or from the water, and you get precipitation of calcium carbonate, which has carbon in it. So we can look at the actual carbon in the rocks themselves. So here is a figure showing the different ratios of carbon 13 to 12. The more negative the number, the more 12 is in the sample. The extinction horizon is noted by the initial isotope excursion, highlighted on the figure there. So there's a big spike. If there's a big spike, that suggests that a lot of carbon dioxide enriched in carbon 12 was pumped up into the atmosphere around the time of the extinction horizon. So this is good evidence. Now, if you're putting a load of carbon dioxide into the atmosphere, you're going to warm it up. Now, you can work out approximately how much carbon dioxide was in the atmosphere before the extinction using that curve, and also evidence from fossil leaves. Now, in the atmosphere before the extinction, about 1,000 parts per million was in the atmosphere. After the event, 2,000 to maybe 2,500 parts per million. To put that into context of the modern day, at the moment, there's about 400 parts per million in the atmosphere. So it was going to be very warm already, and then you make it warmer still after the event. The temperature increase doesn't sound impressive, 2.5 to 5 degrees increase, but that's enough to tip things over the edge. So, evidence for global warming. Tick. Next thing, ocean deoxygenation. That's something that can happen with global warming, with the cascade of effects from the carbon dioxide pumped out by a volcano. Is there any evidence for it in the sections in the UK? Start there. Not particularly, unfortunately. The bed, the sort of boundary itself, is in a very shallow unit. There's actually got wave ripples in it. You can't deoxygenate the water if it's that shallow, because it's just in constant contact with the atmosphere. It's been churned up by waves. It's always bringing in more oxygen. So unfortunately, the actual boundary doesn't seem to have that. That doesn't mean we can't do something else. When I was researching the recovery from the extinction in the UK, I noticed that the diversity, the species richness of shelled mollusks, the bivalves, there's another drop in the diversity. So the first drop is the extinction horizon I've just shown you a picture of with the wave ripple. The second drop occurs later on. And if we look at other sections across the world, we can see a second level of extinction, as indicated here by the little stars. Now, this extinction occurs coincidental with black shales, or the paper shale. Now, that is thought to be an anoxic interval, so an interval when the water column has no oxygen in it, which is what we're looking at, is oxygen depletion in the oceans. Now, there's many different ways you can make a black shale. All it effectively means is it's got a high organic content, giving it a dark color, and that it's a low energy environment, why it's very fine grained and laminated. So is there a way we can look at this and think, is it actually deposited on the seabed and the sea water above it has no oxygen in it? Can we actually test that? We can indeed. Now, there's many different ways you can do it, but the one I particularly like is using these little beauties. These are pyrite framboids. Now, pyrite is fool's gold, and the framboid is this thing in the picture there. They look like raspberries. And they're very, very small. You have to use a very powerful microscope to see these. And the size of them can tell us a bit about what the water column was like in terms of the amount of oxygen in it at the time that these rocks were being deposited. So imagine this little diagram here. We've got the sea floor being the sort of line at the bottom there with the dashing on, and the seawater is the sort of rest of the cube above. The boundary between no oxygen and oxygen, so anoxic, oxic, in this particular diagram is in the sediment, and it's known as the redox boundary, the interval, say, between the interface between oxic and anoxic waters. So it's in the sediment at this point. This is where the framboids grow. They have to grow at this boundary. So inside the water, there is some hydrogen sulphide, and you need that to grow pyrite. And because the boundary is in the sediment, the framboids can grow as large as they like. They just keep growing, and you get a bit of a size distribution that's a bit broad. You have small ones and large ones, but it's very mixed, but you get big ones as well. Now, if that boundary migrates into the water column, so now we've got oxygen depleted waters and no longer in the sediment, actually in the water itself, then the framboids will grow in the water column. There they are. Oh, hey, there we go. Right, now, when they get to a certain size, they sink because they're made of metal, so they're going to sink. They can't sink floating. And once they sink away from that redox boundary, that's it. They stop growing. So if we look at the size distribution of these little raspberries of fool's gold, we can tell roughly where the interface between oxic and anoxic water was. Now, the other crucial thing is it's not only a case of there not being any oxygen in the water, but also the chemical hydrogen sulphide is very nasty, and it has to be free in the water to make pyrite. In fact, hydrogen sulphide is toxic, so it's another sort of double whammy of death in the sea at this time. And this is what a sample looks like if it's an anoxic with free hydrogen sulfide in the water column. All those little specks of white are tiny little pyrite rhamboids. They're very, very, very small, and they've not got much of a size range. So that tells us that this particular sample was deposited under an anoxic water column. And we see that at these boundary beds. So evidence of oxygen depletion in the water, yes. Now, have we got a volcanic province that we can use to put the blame on? We do. We've got one. The Central Atlantic Magmatic Province, also known as CAMP. This is huge. Absolutely colossal. 10 million kilometers squared of volcanism. And here I have again a reconstruction of Pangaea, and in red we've got the volcanic province outlined. Now, unfortunately, a lot of the sort of basalts that were lava that was extruded during this interval has been eroded, and all we can really see are the sort of dikes and sills, the plumbing of the volcano. And here is one, the Palisades Sill in New York, making the cliffs there. Why was this massive volcanic province there? And why do we call it the Central Atlantic Magmatic Province? At the time of the extinction, Pangaea, the supercontinent of Pangaea, was being torn asunder. It was being ripped in half by tectonic forces, and as the crust was thinning, so it was melting, and you were having massive amounts of volcanism welling up in that sort of wound. So there we are, massive volcanism. But did it occur exactly around the time of the extinction? We need to date it. Like we did with the impact craters, we need good dates to correlate these to the extinction. So we've got the different sections, the symbols there show us in North America, South America, Europe or Africa. The error bars, the little sort of whiskers on those plots. And if we look at the date along the top, remembering the extinction occurred at about 201 million years ago, we can see that this eruption series was going on throughout that time, 201 million years ago. So it's a pretty damn good fit. So yes, indeed, we've got a volcanic province. So all in all, it's starting to look very much like the Central Atlantic Magmatic Province was to blame. But can we completely rule out some of the evidence that we've seen for Roche Choix? Remembering it was a very small impact, so it was not likely to cause an extinction anyway. It's just too small. It just can't cause the disruption to the environment needed. But can we pin the Seismite or the Fern Spike also onto CAMP? Start with the Fern Spike. Remembering all that needed really was a major environmental disturbance. You just had to sort of strip the land back of vegetation to cause a fern spike. And just because that happens to have happened at the end of the Cretaceous period, it's been sort of taken as a bookmark for an impact-based extinction. But let's remember the figure, the cascade of effects from a large igneous province. Sulfur emissions can cause the same effect as a volcano. Acid rain as well. That damages plants. Even ozone depletion actually causes damage to leaves. So you could effectively have a fern spike from a volcanic eruption. On a much smaller scale, after Mount St. Helens erupted, the slopes were covered in ferns because they were the first thing to recolonize. So even on such small scales, it doesn't have to be a meteorite. It just has to be some sort of disturbance to the environment. So we can perhaps pin the fern spike on the central Atlantic magmatic province too. What about seismite? Now, is that going to be a bit trickier? Remember this, the bed of shaken up rocks? Well, if you are ripping apart a continent, there's going to be a lot of earthquakes, a lot of ground being upheaved and moved around by tectonic forces. Great shaking could cause the seismite. And also, there's another thing in these rocks that I didn't point out to you before. The bed, the big sort of pale grey bed in the middle, the top sort of honeycomb coloured thin layer, can you see strikes running down vertically from that bed into the pale grey unit below? I'll highlight them in red. These are big cracks in the rock. They look a bit like mud cracks, sort of on a hot day you'd expect to see them in a muddy puddle, but they're too big. They run too deep. This could be other evidence of the upheaval of the land at the time. It's cracking as it's been moved around. So we can probably pin the seismite and also those cracks onto earthquakes and the shaking up of the land that would have been associated with the volcanic province. It's not looking good for the Central Atlantic Magmatic Province. In fact, I think we can probably pass a guilty verdict on that. Well, that's the extinction. But what happened afterwards? It's all doom and gloom. But life bounces back. How was it after the extinction? Well, things weren't quite back to normal immediately. The global warming went on for a long period of time, and some areas experienced anoxic waters for a long time afterwards. They came in pulses, but they didn't cause a mass extinction like the first bed of black shale did. And this could be because they weren't as widespread. This is a section in Wales. It's the same age as the image we've shown you with the black shales on. And there isn't a single black shale in this whole succession. So any animals that live across the other side of the Bristol Channel, as it later became, would have been absolutely fine. And then when the oxygenation reoccurs in the Somerset Basin, from the picture we've just shown you in the previous slide, they just go back and live in that bit of water. So you don't really end up with this mass extinction again every time you get a shale bed, which is rather good. And that allows life to start to persist and start to get better. So back to Lyme Regis, you can see evidence of good late stage recovery in the ammonite pavement. These are big ammonites and there's lots of them, so they must have been doing well, considering this extinction left you with one group of ammonites left. They radiated and they evolved to massive sizes pretty damn quickly. And it wasn't just the ammonites that grew large after the extinction. Some of the bivalves, the clams and whatnot, they grew quite big. These pictures here on the left of the screen is Plagiostoma giganteum. The bottommost image is from just after the extinction. And the top one is only a couple of million years later. It's the same species, it's just the environment has improved to a level that allows them to grow larger, live longer, grow quicker. They're doing a lot better. It's an indication of a much healthier environment. And here's a little reconstruction of the Lyme Regis seas a few million years after the event. It's back to looking healthy, a good structured population. You've got big fish and you've got crinoids and sea lilies on the side there. You've got all sorts going on, and it's a much healthier structured environment with nice diversity. and no one species dominating, which can sometimes happen after an extinction event. So there you have it. So all that remains is me to thank you all for watching, and you can contact me on the various social media accounts at the bottom of the screen there. Thank you all.